Hello everyone. Today we shall discuss about the physics of flow, applications of Bernoulli's principle from aerodynamics to adheres, how fluid dynamics shapes our world. Fluid dynamics functions as the invisible architecture of movement. This presentation explores how a single fundamental rule governs phenomena as diverse as heavy lift flight, atmospheric weather patterns, and human physiology. What Bernoulli's principle says that P1 plus half rho V1 square plus rho g H1 is equal to P2 plus half rho V2 square plus rho g H2. This is the Bernoulli's principle. Whenever there is high velocity, the pressure will be low. When the velocity is low, the high pressure. And here also lift, in the case of airplane also, you see here in this case all the air blows in a curved surface. So the velocity at this position is more than the lower end. So when the velocity is high, it creates a low pressure zone. It creates a low pressure zone. And here you see, in this case, the speed is low. So here creates a high pressure zone. So there is a lift of this airplane in the upward direction because it moves from high pressure to low pressure. In this direction, upward, and that is the lift of airplane, or what we call is aerodynamics. In case of fluid also, in case here, fluid means in a pipe. Suppose the area is low, but the velocity is high in this case. When the velocity is high, it creates a low pressure zone. When the velocity is low, in this case, it creates a high pressure zone. And it moves from high pressure to low pressure. So it moves in this direction, high pressure to low pressure. And this is what governs the various activity of our earth. The inverse relationship is speed versus pressure. I already told you, when the speed is more, pressure is less. Inverse relationship, that is, speed is directly proportional to 1 by pressure. What is the meaning? The inversely proportional to pressure. That means when the speed is more, pressure will be less, and when the speed is less, pressure will be more. You see here what we get here: high pressure, low velocity, slow speed. And here you see high velocity, so there creates a low pressure zone in this area. Low pressure zone. Here also you see slow speed, so it is a high pressure zone. So what is the rule? The rule: when fluid energy is directed into speed, kinetic energy, the pressure it exerts on its surrounding potential energy must decrease to conserve total energy. That is our rule. When fluid energy is directed into speed, kinetic energy, the pressure it exerts on its surrounding potential energy must decrease to conserve total energy. Bernoulli's principle defines this fundamental trade-off. Faster moving fluid exerts lower pressure. Faster moving fluids exerts lower pressure. This intuitive rule is the foundation for understanding lift, flow measurement, and fluid control. So all these are defined by the relationship speed is inversely proportional to pressure. And this is what is says in Bernoulli's principle. Next one you see here, conquering gravity in the airplane wing. I already told this one. Here you see the net force lift here also. The speed is very high, high velocity region. Here the high velocity region is here. Air travels faster and faster over curve. So when the velocity is high, it creates a low pressure zone. And here the velocity is low velocity region, therefore it creates a high pressure zone. So there is a net force, high pressure to low pressure, that means in the upward direction. The airfoil shape, the curved top forces air to travel a longer path than the bottom. To rejoin the airflow at the trailing edge, the air on top accelerates. So the velocity is here more. And whenever the velocity is more, creates a low pressure zone. And when the velocity is small, it creates a high pressure zone. So there is a lift in the upward direction of the airplane. Air travels further and faster over the curve. Lift is not just air pushing up from below, it is equally the partial vacuum, low pressure above pulling the wing upward. So lift is not just air pushing up from below, it is equally the partial vacuum, low pressure above pulling the wing upward. And this is governed by Bernoulli's principle. Next, what you see here is the harvesting energy, lift in rotation. Lift force, torque, you can see here. Wind turbines, we have seen the wind turbines. Wind turbines do not work like paddle wheels pushed by the wind. The blades are rotating wings. As air flows over the curved blade surface, you see here, as the velocity at this region is more, creates a low pressure zone here, low pressure. And when the velocity at this position is low, creates a high pressure zone at this position. So as air flows over the curved plate surface, it creates a pressure differential. This lift force is directed forward, creating the torque that drives the turbine, that generator. So it creates a torque, and so it revolves very easily. Lift force, that means creates a torque actually. Harvesting energy, lift in rotation. So wind turbines do not work like paddle wheels pushed by the wind. Their blades are rotating wings. As air flows over the curved blade surface, it creates a pressure difference. This lift force is directed forward, creating the torque that drives the turbine generator. The power of constriction, the Venturi effect. You see, this is what we call it, the Venturi effect. Here the velocity is high. You see here, the velocity is high here. High velocity. Velocity high. Whenever the velocity is high, it creates a low pressure zone. And here the velocity is low. Velocity is low. So it creates a high pressure zone. So here you can see the Venturi effect occurs when a fluid flows through a constricted section of pipe. You see here? To maintain mass flow, velocity must increase. Consequently, static pressure drops. So there is a drop of pressure here. This simple mechanism allows us to use flow of create suction. constriction, acceleration, pressure drop. You see there is a pressure drop here, and this is the Venturi effect, or what you call it, the power of constriction. So there is a pressure drop in this region, del P. This is the power of constriction, or what you call the Venturi effect. Precision instrumentation, Venturi meters. We learn about Venturi meters. In industrial engineering, measuring the volume of fluid moving through a massive pipe is difficult to do directly. So, Venturi meters solve this by measuring the pressure difference caused by a constriction. Because the pressure drop is proportional to the square of the flow of the speed, because the pressure drop is proportional to the square of the flow of speed, engineers can calculate precise flow rates instantly. Quantity A, Q is equal to A root over 2 del P by rho, where rho is the density of the liquid. So, precision instrumentation, this is Venturi meters. In industrial engineering, measuring the volume of fluid moving through a massive pipe is difficult to do directly. Venturi meters solve this by measuring the pressure difference caused by constriction. Because the pressure drop is proportional to the square of the flow speed, engineers can calculate precise flow rates instantly with the help of Venturi meters. Aspirations and atomization, mixing fuel and air. Combustion engine carburetor. This is combustion engine carburetor. This is perfume atomizer or sprayer. First we are dealing with this one. You see here that high velocity here. When the velocity is very high here, at this position, it creates a low pressure zone. Liquid perfume, low pressure zone, so it goes up. High velocity means it creates a low pressure zone, and so from high pressure to low pressure the liquid moves up, and this is the working of a sprayer, or what we call it as atomizer. You see, when the air blows here, high speed of air, and then when the speed is high, pressure is low at this position, so the liquid flows from high pressure to low pressure in this direction. This is the work of a perfume atomizer or sprayer. Combustion engine carburetor. This is Venturi throat. This is high velocity air. This is low pressure fuel. So both devices utilize the same principle. High velocity air creates a localized low pressure zone. This partial vacuum acts as a pump, drawing liquid, fuel or perfume. Here you see drawing fluid. Here is a high pressure zone. Here is a high speed, high velocity air. So there is creates a low pressure fuel, and Venturi throat, so the oil moves up. Both devices utilize the same principle. High velocity air creates a localized pressure zone. This partial vacuum acts as a pump, drawing liquid, fuel or perfume up from a reservoir to mix with the air, creating a fine mist. This is the principle for atomizer or combustion engine carburetor. Next important is bending the trajectory or sports physics. This is very much important, sports physics. What is that? And it is also known as Magnus effect. Here you see when the ball revolves in this way, so the velocity adds up. This is first air. When there is first air, when the velocity of air is fast, at this region it creates a low pressure zone. Low pressure zone. And here you can see the velocity slow air. Here the slow air, so it creates a high pressure zone. High pressure. So there is a lift in the upward direction, Magnus force, or what we call it as Magnus effect. The Magnus effect is Bernoulli's principle in action on the field. A spinning ball drags a boundary layer of air with it. On one side, this spin aids the airflow, low pressure. On the other, it opposes it, high pressure. Here, the velocity adds up. Right? So what you get, on one side this spin aids the airflow, low pressure. On the other hand, it opposes it, high pressure. The ball is pushed toward the low pressure side, creating the curve in basketball, cricket or soccer. So it moves, and this is known as Magnus effect. The Magnus force is in this direction, so it moves a little bit. This is known as Magnus effect in Bernoulli's principle. Besides that, we can find other things also, that is the danger of proximity, ship design and interaction. Maritime plots, here you see when the two marines goes here, the water between the two ships, velocity is high, so it creates a low pressure hazard zone. What happens? Maritime pilots must account for hydrodynamic interaction. When two large vessels pass closely, the water channel between their hulls accelerates to pass through the gap. The resulting drop in pressure creates a suction force that pulls the ships together, presenting a significant collision risk. So the danger of proximity, ship design and interaction. It creates a low pressure zone. So it is very dangerous for two ships to move closely with each other. So there is a collision risk factor come here. Because when the liquid flows, velocity of this liquid is very high, so it creates a low pressure zone. And in the here you see here the water velocity of water is low, so it creates a high pressure zone here, high pressure. Here high pressure, and upward also it creates a high pressure zone here, high pressure, high pressure. So there is a force in this direction and there is a force in this direction. So the two ships will collide with each other. Internal dynamics, blood flow and arteries. This is also very important. Peak velocity, lowest internal pressure. Here you see peak velocity, lowest internal pressure. Hemodynamics. In a stenotic narrowed artery, blood must accelerate to pass the blockage. Counterintuitively, this high velocity drops the internal pressure against the artery wall at the precise location of the blockage, which can contribute to vessel collapse or further structural issues. When there is a high peak velocity, here the lowest internal pressure is reduced at this point. Whenever there is a blockage, there is a reduced pressure here, high velocity, accelerates it. Internal dynamics. Hemodynamics. In stenotic narrowed artery, blood must accelerate to pass the blockage, this one. Counterintuitively, This high velocity drops the internal pressure against the artery wall at a precise location of the blockage, which can contribute to vessel collapse or further structural issues. Atmospheric forces, tornadoes and roof lift. Tornadoes and roof lift. You see, stagnant air, high pressure. Net upward force, you see high velocity, that means it creates a low pressure zone at this position. Tornado formation, similar principles apply. Rising warm air creates an intense low pressure core around which high speed winds organize. During hurricanes, roofs are rarely blown down, they are sucked up. The fast moving wind over the peak shape creates a low pressure zone. Here the low pressure zone and inside is high pressure zone. So there is a lift in the upward direction. While the stagnant air inside the house pushes outward and upward, and with the normal atmospheric pressure lifting the structure, and it blows out. So this is the atmospheric forces in case of tornadoes and roof lift. The roof lift upward in this case according to Bernoulli'S principle. Advanced frontiers, acoustics and oceanography. The principle extends beyond steady flows into complex, unsteady environments. In acoustics, it helps model how sound waves propagate through fluids. In oceanography, it is fundamental to understand the pressure dynamics within rolling waves and currents. You can say that is sound wave. This is static pressure. The principle extends beyond steady flows into complex, unsteady environments. In acoustics, it helps model how sound waves propagate through fluids. In oceanography, it is fundamental to understanding the pressure dynamics within rolling waves and currents. The universal rule of fluid dynamics. Transport. So these are the various conclusions of this rule of fluid dynamics. Transport, lift generation, wing design, drag reduction. In case of measurement and control, eventually measures, calculators, atometers or sprayers. Motion and safety, magna-sphere sports, ship collision avoidance. Nature, arterial blood flow, tornado, weather patterns, all these will be governed by the Bernoulli'S principle. From the micro scale of fuel injection to the macro scale of atmospheric storms, the inverse relationship between velocity and pressure remains constant. The inverse relationship between velocity and pressure remains constant. Understanding the invisible. Bernoulli'S principle is more than an equation. It is a lens through which we understand the mechanics of the world, whether it is the vast force lifting a jet or the microscopic flow of medicine. The rule remains velocity dictates pressure. So what we get at the end, that velocity dictates pressure. When the velocity is high, there is creation of low pressure zone. Thank you everybody for watching this video.